So we're going to talk about this a lot. So again, I really like inverting linear systems just because, so first of all, it's interesting in its own right? Linear systems do come up in practice quite often. And also, even if you're interested in things like eigenvalue problems or nonlinear problems, there are similarities or they reduce to solving linear problems. So how do we solve this kind of things? So we've seen yesterday, we've seen algebraic methods of resolution. So Gaussian elimination, LU decomposition, all these kind of things. So they are n-cubed, and therefore they do not work for large systems. So what techniques do you have? So first, one technique that is useful. So today I'm mostly going to talk about iterative methods for solving this kind of problems. But before I do that, I would just want to briefly mention what happens with specific structures, specific matrices. So one thing that comes up a lot is when you have a partitioning. Of your system. This comes up a lot in quantum mechanics, where, for instance, you'd have a system that is decomposed in some kind of subsystem of interest and some kind of environment, for instance. Or, I mean, there are really a lot of instances of problems like this. So if you have a problem like this and you want to solve AX is equal to B, how do you do? Well, you use essentially Gaussian decomposition. But Gaussian decomposition, Gaussian elimination, but block the. So okay, so this is these are two subsystems of size n1 and n2, and I want to invert this. How do I do? Well, I use block Gaussian elimination, meaning that I just like you would do for Gaussian elimination, but instead of subtracting A21 over A11 to this line, then you do this in a block way. So another way of seeing this is just writing out this equation and seeing it like this. And then I solve for x1 as a function of x2. Okay? So from these two, from the first equation, I get that x1 is a11 minus 1, assuming, of course, that this guy is invertible, times b1 minus a12 x2. Okay, so that gives me x1 as a function of x2. So this is like a merge of the two steps of Gaussian elimination. And then I plug this back into this equation. And what do I get? I get a21. So if you merge everything together, you get a22 minus a21, a11 minus 1, a12. So with this partitioning, it's nice to check if these formulas make sense because these indices have to match, right? You have to contract the 1 with the 1 here and so on. So this times x2 is equal to b2 minus minus a11 minus 1b1. Okay, and now you can solve for x2. And this matrix that appears is called the Schur complement of the matrix, assuming that you can invert this block. Of course, I mean, you can do it the reverse. You can invert A22 and get another Schur complement. So Schur complement come up a lot, many contexts. Essentially, whenever you have a partitioning of your system into two subsystems, you can bet that the next thing you're going to write on your page is a complement. Yes. Yes. Thank you. Okay. So this is useful in a number of contexts. So for instance, if A11 is simple to invert, maybe it's a diagonal matrix, maybe it's the identity, maybe something like this, then you get a reduced equation, which is much simpler, right? Which is smaller. You invert and you plug back. So of course, then once you get x2, you can plug back and get x1. It's very simple. So this is also useful in a number of contexts. For instance, you can prove things like if A11 is invertible and if this short complement is invertible, then the matrix is invertible. Okay, this is the proof, right? You can just get x2 and then plug back into x1. You can show that if A1 is symmetric, definite positive definite. And if the short complement is also, then the whole matrix is positive definite. This is also useful for a number of things. So one application, of course, we are in a chemistry, in a quantum physics public, so we love eigenvalue problems. So eigenvalue problems, you can play the same trick. Assume that you've got a matrix, which we'll call H now because it's Hamiltonian. And I do it this. Okay, I can play the same trick. And what I will get is, what will I get? I will get H22 minus lambda minus H11 minus lambda minus 1 H12 is equal to 0. Okay. Times, of course, x2 equal to 0. So in other words, H22 minus H21, H11 minus lambda minus 1, H12 times x2 is equal to lambda x2. So what do I get? I get an eigenvalue problem for x2. Okay, so in typical applications, the second part would be the thing you care about. Okay, maybe you have a molecule embedded in some other some solvent or something like this, and you are interested in the molecules. So the molecules are your n2 degrees of freedom, and you're looking for an effective equation for the subsystem. Okay, and here's your effective equation. You have something that looks like an eigenvalue problem, but it has a nonlinear part. You've seen that this depends on lambda. So this is called sometimes, okay, I'm not claiming that this is the right thing, but this is like a self-energy. This is something that gets added to your Hamiltonian into an effective equation. So this whole thing is an effective Hamiltonian, and this is like a self-energy. Okay. So of course, in actual context, you do many body things, so it's not exactly this that you have to solve. It's a many body thing with a tensor structure and so on. So it's a bit different, but the basic algebra is this. Okay, so here in a very, very simple context, you see this kind of structure coming in. So for instance, with this kind of things, you can prove things like Fermi's golden rule, which is always confusing when you have continuous spectrum. And when you do this, you have to be careful because you have to take limits in the right order in the complex plane and so on. But essentially, you get, for this guy here, you get an imaginary part, which is the lifetime, the inverse lifetime of the state. Okay, I'm not going to talk about this. It's a good way of saying it. Good with this. So this is sometimes called, so this is called floor complements. It has a lot of names because it has been rediscovered a lot and lots of times. This kind of things is called Fano, Feshbach, Fano, Feshbach Schur, Feshbach something. Okay, Schur plus Feshbach plus some other names sometimes.
In quantum chemistry, it's also known as Love-Din partitioning.
Everything is known as Love-Din in quantum chemistry. So
yeah,
okay, so Love-Din partitioning is this or
yeah.
Okay. Right. So Love-Din, Schur, Fano, Feshbach. Yes. Okay. Sherman-Morrison is different, and I'm going to talk about Sherman-Morrison now. So it's related, but it's not really this partitioning thing. You don't have separate degrees of freedom. So Sherman-Morrison is this. So Sherman-Morrison is you have a matrix A, but you don't split into two sets of degrees of freedom. You have a matrix A, and you add a low-rank matrix. Okay, we've seen with Misson what is low rank and so on. So this is a rank 1 matrix, but it also works for low rank. Right? So this is this plus something. Yeah. Yes. So yeah, you have to split your thing into U here and some part that is on the orthogonal of U, and then you can rewrite this as a Schur complement. Yeah. Yes, but it's not completely natural. So in particular, when you have UV transpose, it's a bit more messy to do this. But yeah, I agree. It can be done with Schur complement. Everything can be done. This guy. Okay, so this is Fesh. So this is an S, this is Feshbach, this is Schur. So the most important name is Schur complement. Okay, this is Feshbach Schur, Feshbach Fano partitioning. So probably Feshbach Fano is in physics, and this is Love-Din is in chemistry. Yeah, Fano. It's used in the study of Fano resonances and things like this. Anyway. Okay, so this is Schur complement and so on. This is Sherman-Morrison formula. Not sure about the number of N's and S's, but related to that, okay? It's also Woodbury. So Woodbury is when you have a more than rank 1 matrix. So you have big matrices, U and V transpose. Just one S. Reason. The formula is what? Yeah. So I'm not finishing because I don't know this by heart. The point is what is this? How do you get this? So either you look it up on Wikipedia or you try to get an idea. So of course, the important bit is that okay, I don't know my hand. Yeah, so here I'm doing it in the Hermitian case, but yes. No, but it's right. You're right. Let's do it in the general case. So why is this important? It's important because this includes things like you have a matrix, you have a big matrix, you've done a lot of work to invert it, and now you change one column, for instance. Changing one column is a rank 1 perturbation. Okay, this column here, this changing of a column, I can write it as U EI transpose. Okay, so if I change a column, if I change a row, if I delete a row, if I delete a column, you can write it in this way. So this is important in a number of places. For updating factorizations, for instance, is also important. So if you want to do DIS in a fancy way, you can update your factorization with these kind of things. Yeah. Yes, this is what you are, but this I don't know. But apparently, yes. So in Monte Carlo, because you update slaters. Okay. Yeah, because of course, this you can also use to compute determinants. Right. So what is this formula? So how do you get this formula? So one solution is exactly to do what Roland said, to see it as a Schur complement. Another way is to pretend that there's a small parameter. Okay, and to do an expansion. So if I just do this, I do an expansion, I get, what do I get? I get this, first order, okay? Minus plus epsilon squared over 2, no over 2, plus epsilon squared u a minus 1 u v transpose a minus 1 u v transpose a minus 1 minus etc. Okay, and then what can you do with this? You can resum, because you can factor out that this is a minus 1 minus a minus 1 u a minus 1 v transpose. And what do you have there? You have epsilon, just epsilon, plus epsilon squared a minus v transpose a minus 1 u plus etc. And you find out that this guy, did I mess up on okay, so I put the epsilon here. I get 1 plus epsilon that plus with a minus. No. Okay. And so now this guy I can resum, and this is just 1 over 1 plus epsilon v transpose a minus 1. Okay. And that's the Sherman-Morrison formula in the end. So you get, this factor does not matter too much. You get a minus 1 minus, so this is a vector, right? This is a vector transpose. So you see that the inverse of a rank 1 perturbation of a matrix is a rank 1 perturbation of the inverse, right? The inverse of that guy is that guy plus that guy, something which is just a scalar. That guy transpose. Yes. It's yes, 6 1. It's also a minus transpose v transpose. So is this actually correct? So this is true for epsilon small. Why is this true for epsilon small? This is Neumann series. Right? So this is true if the norm of A is strictly smaller than 1. And so more generally, if the spectral radius of A is smaller than 1, you can find a norm such that this is true and this holds true. Yes.
The interesting thing about having a rank 1 matrix,
yes,
is because essentially you can factorize stuff and end up with just the scalar, this 1 over 1. And so what if you have not a rank 1 matrix?
So if you have a rank 2 matrix, the inverse of a rank 2 matrix of a rank 2 perturbation is a rank 2 perturbation of the inverse. Yes, yes. So if you do this in the general case, so U and V get to be matrices now, and this you replace by 1 plus epsilon V transpose epsilon minus 1 U minus 1. So you have a small matrix that you have to invert. It's tractable. It's relatively cheap. So Sherman Morrison is with rank 1. Woodbury is with rank n. It's the same algebra. Okay? So now I'm trying to justify why this formula would be true. So this formula is true for epsilon small. It's true for epsilon small because this identity holds, and this holds because it holds for scalars, and then you can. It holds for any algebra, any Banach algebra. Okay, so this is true, and therefore this is also true. The expansion, okay, I'm not going to write it, but you know what it is. The expansion for A minus epsilon B, you just factor out A minus 1, and you get the expansion that I use there. And this is true whenever the norm of A minus 1 times B is smaller than 1. Okay, so clearly if epsilon is small enough and my matrix is invertible, then this is good. Why should it be true for epsilon is equal to 1? So, okay, I want to prove this formula for epsilon is equal to 1 because I don't want to limit myself to small epsilon. I have proved this formula for epsilon small. Why is it therefore true for epsilon is equal to 1? No, well, it's not small. Chemist. It's an analytic function. So yes, so whenever you have an equality between two things that depend that depends analytically on a parameter, then the things are always equal. Even okay, well, okay, this is not complex analysis, but when you have a function, an analytic function that is 0 in some neighborhood, in some region of space, is 0 everywhere. Right? So two functions that are equal for epsilon small are equal for epsilon big. As soon as you don't have too much singularities between them. Okay, but this is okay because if you look at this, so of course it can happen that maybe you're interested in what happens at epsilon is equal to 1, and you know what happens here. You know that here for epsilon small enough, this formula is valid. So you can continue it analytically, but you can continue it analytically whenever you don't encounter singularities. And here you have singularities when this guy becomes 0. So it can happen that you would have a singularity here. Okay, maybe at that point, 1 plus epsilon V transpose A minus 1 U becomes 0. So then you cannot continue it analytically here, but you don't care because you're in the complex plane. So you can just continue analytically like this. Okay, so now you have two things that are analytic and that are completely well defined on this path, and that are equal at the beginning, and therefore they are equal for the whole path, and therefore they are equal at 1. Yes. Yes. Oh yeah, of course. If at epsilon is equal to 1, this is this is 0, then of course this formula doesn't make sense because A is not invertible in this case.
So what you're saying is that it is true everywhere.
Except when except when the matrix is not invertible. Yeah. So for this formula to be true, with epsilon is equal to 1, you need A to be invertible, and you need this guy to be non-zero. And so in the general case, in the Woodbury case of rank n, you would have something similar, but you would have maybe many places where this matrix is not invertible. Okay, but these are discrete singularities, and you can always continue between discrete singularities. So the fancy name for this is analytic Fredholm theorem. Let's not bother with this. Okay. You agree? So the same kind of proof. So of course, I mean, this is just because I wanted to show off fancy complex analytic techniques. But of course, if you don't care about this, if I just give you this formula, you can just check that this times this is 1, and you get the results. But this is not fun. It's really not fun. But basically, you're just mimicking this proof with the telescopic sum. Okay. But this kind of fancy technique of perturbative techniques is interesting because it's very natural, of course. If you're a chemist, you really like small parameters. And also, it can be useful for other contexts. For instance, if you want to prove that AB has the same non-zero eigenvalues as BA, you can use a technique like this with resolvents and continuation. Yes.
Can you say again the name of the
Sherman Morrison.
No, the fact that it's equal for any epsilon. Analysis.
This is just the fact that the complex analytic function has that cannot be. Yeah. So Fredholm. This is for when you got a single singularity, it's very easy to see. Otherwise, it's called Fredholm. Analytic Fredholm. So analytic Fredholm is a very fancy thing for saying that a determinant is an analytic function. And therefore, if you have a matrix here, the places where this guy is singular are the places where the determinant is 0, and these are isolated singularities. But this extends to operators where the determinant might not be well defined. It's compact operators.
I think also is that you can use this as so if you are interested in the trace of the universe, it provides you an update also of the trace of the universe.
Yes, of the trace, of the determinant, of a lot of things. Yes. Yes. I missed an epsilon where? Sorry. Thank you. Okay. So this is done for algebraic methods of resolution of equations. And now we get to the analytic stuff. We get to iterative methods. Any questions on this bit? So I think it's interesting to present this kind of things in a general context because they very, very often come up in specific forms in practice. And in specific form, it might not be super easy to see that really it's a very simple idea with a simple core. Okay, so now I still want to solve Ax is equal to B. This is my life. But I don't want to assume a specific structure on A. I just want to assume that A can be applied efficiently to a vector. So for instance, A is sparse. So I have this huge matrix that is some discretization of my Galerkin problem, comes from application, like a partial differential equation, something like this. And I really, really want to solve Ax is equal to B. So Gaussian elimination is out because this is too expensive. So I'm going to try numerical methods. What can you do when you have a matrix that's so big? Not a lot. You can take vectors, add vectors, multiply A with a vector, multiply vectors by scalars, but there's not a lot you can do. So if I have X, I can compute AX. And from this, a very important thing to compute is the residual AX minus B. So what can you do when you don't know what to do and you just have a vector and you can just compute residuals? Well, you take your vector and you add the residual. So this method is Richardson's method. This is Richard. Do not use this in practice. This is not for using in practice. This is for doing math. I will then explain what people should do in practice, but this is not what you should do. But understanding this is very important to understand the more sophisticated methods. So what is this algorithm? It's also the same as gradient methods. If A is S ED,